Welcome to Easy Physics classes. Question number 1.7. An electrostatic field line is a continuous curve. A field line cannot have sudden breaks. Why not? Sub-question B. Explain why two field lines never cross each other at any point.
We all know that gravitational field is always associated with masses. Similar to that, electric field is always associated with charges. Gravitational field is a space around a mass where gravitational pull can be experienced. Similarly, electric field is a space or a region around a charge where electrostatic force or influence of that charge can be experienced by any other charges. Electric field, it is the space around a charge where its influence or electrostatic force can be experienced by other charged particles or objects. Electric field intensity vector E gives the strength or intensity of electric field at a particular point. It is defined as electric field intensity at a point in space is defined as the force experienced by a unit positive charge placed at that point. Here, suppose this is a particle which is having a charge plus q, and we want to find out what is the intensity of electric field produced by this charge at this point, that is at P. So, what we have to do, we have to imagine a plus 1 coulomb charge is placed here and find out the force experienced by that charge. Electric field intensity is the force experienced by a unit positive charge placed at that point. So, here we want to find out what is the electric field intensity. So, find out what is the force experienced by this unit positive charge. Then force will be K Q1 Q2 by R square, that is K Q1 is Q, Q2 is 1. So, by R square, so you will be getting K Q by R square. Now, the direction of electric field is same as the direction of force experienced by this unit positive charge. That means, this unit positive charge will get repelled by this charge along this path, that is along OP, that is written here. So, vector E equal to KQ by R square along OP. In SI system, vector E equal to 1 by 4 pi epsilon 0 Q by R square along OP. Here we have taken epsilon 0 to show that there is no medium or the given medium is air. So, that is electric field intensity of a point charge. So, this equation is only applicable for a point charge. Magnitude of electric field produced by a point charge at point P, which is at a distance r from the point charge, will be E equal to 1 by 4 pi epsilon 0 Q by R square. This is only valid for a point charge. Now, if the charge distribution is like this, that is, it is a line charge distribution, or like this, there is a surface, so it is a surface charge distribution, then the equation for electric field intensity will be different, that we will be discussing later. Electric field intensity is defined as the force experienced by a unit positive charge, or it is the force experienced per charge, or it is equal to force divided by charge. It is a vector quantity. SI unit is Newton per coulomb. Electric field intensity is the term used to represent strength of electric field mathematically. Now, another term, that is electric field lines or electric lines of force. These are imaginary lines or theoretical concept used to represent electric field. Now, what is the definition of electric field lines? These are curves along which a unit positive charge would tend to move when free to do so in an electric field, and the tangent to these curves at any point gives the direction of electric field at that point. Or simply we can say it is the path followed by a unit positive charge when it is placed in an electric field. So, electric field lines, we can simply say it is the path followed by a unit positive charge when it is placed in an electric field, when it is placed in an external electric field. Now, the tangent to electric field lines at any point gives, that is an important point, the tangent to the electric field lines at any point gives the direction of force experienced by a unit positive charge at that point. So, electric field lines are curves that is path followed by a unit positive charge if it is placed in a if it is placed in an external field, and tangent to the electric field lines gives the direction of electric field at that point, or it is the direction of force experienced by a unit positive charge at that point. Electric field lines or lines of force. This is an imaginary concept or theoretical concept which was introduced by Michael Faraday to visualize the nature of electric field of a charged particle or a body. It is simply, we can say, it is simply the path followed by a unit positive charge. Whenever you want to draw the electric field lines of a charged body or a particle through a particular point, you have to imagine that a unit positive charge is placed at that point, and then draw the path followed by that unit positive charge. Then you will get the electric field line through that point. Imagine that this is an electric field line along which this unit positive charge is moving. To find the direction of electric field at this point, I am drawing a tangent here. So this tangent will give the direction of electric field at this point. Now if you want to get the direction of electric field at this point along the curve or along the electric field line, you have to draw a tangent here. So this tangent will give the direction of electric field at this particular point. At any point along this electric field line, if you want to get the direction of electric field, you have to draw the tangent. Now each tangent is having different direction. That means at each point the direction of electric field will be different. So that means at a particular point electric field is having only a single direction. Now let's see how the field lines of a positive charge is drawn. Now imagine that this is a positive charge or positively charged particle having charge Q. Also imagine that this is a point charge. Now to draw the field lines of this charge, imagine that at this point plus 1 coulomb charge is placed. Now what will be the direction of force experienced by this plus 1 charge? We all know that this is also a positive charge, and this positive charge will repel the plus 1 charge or plus 1 coulomb along this direction. So that means the direction of electric field at this point will be away from both the charges along the line joining them, that is along this direction. Similarly, if you want to find the direction of electric field at this point, imagine a plus 1 coulomb charge here and look into the direction of force experienced by this plus 1 coulomb charge at this point. This plus 1 coulomb will get repelled by this plus q charge along this direction. So that means that will be the direction of electric field line through this point. Similarly, if you want to find out the direction of electric field at this point, place a plus 1 coulomb charge here, look into the direction of force experienced by this plus 1 coulomb charge. So we get an idea that how the field lines are drawn. So it will be like this. So this plus q charge will be having field lines which is diverging away from the charge like this. Similarly, if you want to draw the field lines of this negative charge through any point, then you have to imagine that a unit positive charge is placed at that point and find out the direction of force experienced by this unit positive charge. So I assumed unit positive charges are placed like this. From this it is clear that the electric field lines of this negative charge will be directed towards the negative charge, and it will be spherically symmetric like this, because all the positive charges will get attracted towards the negative charge. If you consider this charge, it will move along this path. If you consider this charge, it will move along this path like this. So that means these are the electric lines of force of this negative charge. So these field lines are spherically symmetric, just like that of the positive charged particle. The figure shows the field lines of two equal and opposite charges. Two equal and opposite charges separated by a very small distance is called dipole. So imagine that this is a dipole, because it is a plus q charge and minus q, so they are equal but opposite in nature and separated by a very small distance. So it is a dipole. Here the positive charge will repel the unit positive charge placed at any point, and negative charge will attract that unit positive charge. So if you place a unit positive charge here, it will repel, this plus q will repel this unit positive charge, but it will attract, so it moves along this path. So that is how we get the field lines of this dipole. That means electric field lines start from positive charge and end at negative charge. So this is another example, field lines of two equal and positive point charges. Here the field lines are like this as shown in the figure. I will explain. If you want to get a field line through this point, you have to place a unit positive charge here. This plus q charge will repel this unit positive charge. Also the second positive charge, that is this plus q, will repel the same unit positive charge placed here. So it will move along this curve. Similarly, we have drawn all the other lines of force. So this is how you are going to get field lines for two equal and positive point charges. This point where there is no electric field line or where there is no electric field is called neutral point. Instead of these two positive charges, if you are placing two negative charges, the field pattern will be same, field lines will be same, but direction of this arrows will be towards the negative charges. That will be the only difference. We are going to discuss some of the important properties of electric field lines. Electric field lines are continuous curves without any breaks. No two field lines will intersect each other. The lines of force starts at positive charges and end at negative charges. They cannot form closed loops. If there is a single charge, lines of force start or end at infinity. The relative closeness of field lines gives the measure of strength of electric field at that region. Electric field lines are always normal to the surface of a conductor. Electric field lines does not pass through a conductor. Electric field lines are continuous curves without any breaks. Imagine that there is a charge plus q which is having a field like this. Up to here there is electric field, then again break, then electric field will be there, then break, like that. Now I am placing a positive test charge in this field, then what happened to this charge? This charge will experience a force by this formula, that is F equal to Q0 into electric field intensity. So up to here it will experience a force, and up to here it will accelerate. Then from here to here it moves with uniform speed or uniform velocity. Then again it will accelerate, then uniform speed, then again accelerate, like that. So we feel like the charged particle is jumping from one point to the another point. That means up to here the particle will accelerate, then jump, then from here accelerate, then jump, like that. But actually it is observed for all the cases that in an electric field the charged particle is accelerating continuously. No jumping is there. That means electric field line does not have any breaks. It is continuous. Field line will be continuous like this. It will not have any break. That is, if the field lines are having breaks, then the charged particle placed in the electric field, in that electric field, will jump from one point to another. But the motion of a charged particle in an electric field is observed to be continuously accelerating. That is, electric field line does not have breaks. Property: no two field lines will intersect each other. Imagine that these are two field lines. They are intersecting at this point. If they intersect, we can draw two tangents A and B, and tangents represents direction of field intensity at this point. But we know that electric field intensity at a particular point on an electric field line will have only a single direction. If they intersect at this point, we will be having two directions, so which is not possible. That is, if two field lines intersect, then at the point of intersection, two tangents can be drawn indicating two different directions of electric field at a single point, which is not possible. Next property: lines of force start at positive charges and ends at negative charges. They cannot form closed loops. If there is a single charge, lines of force will start or end at infinity. Examples: if we are having positive and negative charge like this is a dipole, then we know that this lines of force is starting from positive charge and ending on negative charge. But here this is only a single charge here, that is plus q. So the lines of force are moving towards infinity. Here the lines of force are coming from infinity towards this charge. Fourth property, the relative closeness of lines of force gives the measure of strength of electric field at any region. If the lines of force are close together, then it represents strong field. If the lines of force are far apart, it represents weak field. If they are parallel and equally spaced, then it represents uniform field. Like this. Here the field lines are close together. Here it is far apart. That means here the field intensity is weak, or here the field is weak, here the field is strong. Now these are equally spaced parallel lines which represents uniform electric field. That means intensity is same everywhere. Here intensity will be less, here intensity of electric field will be more. Okay, the fifth property, electric field lines are always normal to the surface of conductor. Imagine that this is a conductor and we are having electric field like this. If we are having an electric field vector which is at an angle theta to the conductor, then we will be having two components. One is E sin theta and E cos theta. That E cos theta is along the surface of the conductor. So that means there is an electric field along the surface of the conductor. So the charged particle along the surface of the conductor will experience force, and there will be a current flow without applying any voltage or potential difference. That is not possible. So that means electric field cannot be like this. It will be always normal to the surface. Sixth property, electric field line does not pass through a conductor. That means if there is no electric field lines inside the conductor, electric field inside the conductor is 0. Since there is no electric field inside the conductor, there won't be any electric field line through the conductor. So far we have discussed all the theory portion related with this question, and the answer to this question is property 1 and 2 of electric field lines, which we have discussed earlier.
Thank you for watching. Please subscribe our channel for more updates. Since the NEET and JEE exam dates has been published, we'll be discussing questions based on NEET and JEE patterns in the coming videos. Please watch, share and subscribe.